Hi everyone, welcome back to my channel. Today we will be discussing the topic of rejection sampling. And let's describe the setup here, right? So first of all, we are given an unnormalized PDF, right? So maybe the distribution that we want to sample from looks a little bit like this, and what is given is its unnormalized density, so p tilde of x. So this unnormalized density is only off by some normalization factor. So if we divide this by z, this will give us the normalized density, and the idea is that over the entire support, let's say if it's minus infinity to infinity, there's normalized density which sum to 1, but this unnormalized density doesn't sum to 1, and that's what we're given, right? So this is given. Okay, now the goal is, or the process rather, involves choosing a proposal distribution, right? So there's a proposal distribution, let's say that is q of x, and essentially q of x is another distribution which is like an envelope over this original distribution. So that's the only requirement. Our q of x should cover the original desired distribution at all points, and if we cannot sample from the original distribution, then we can sample from q of x and follow a procedure to get samples from the original p of x, right? So the condition is that q of x times a constant, let's say m, should be greater than or equal to p tilde of x. So that's the requirement, right? You should be able to choose a q of x such that for a specific constant it always is greater than or equal to the unnormalized density, right? And so to ensure this, q of x should not be 0 where the unnormalized density is positive, right? So what you should ensure is that, for example, if this distribution, let's say, becomes non-zero here, then your proposal distribution doesn't drop to 0 here, right? And that's the setup. All right, so before we continue with the process, let me assert the fact that we are given p tilde of x, which means that we cannot really sample from p tilde of x, but we can evaluate p tilde of x for any x, right? And similarly for q of x, where we have to choose that, and basically we should choose something that we can both sample from and evaluate as well. So evaluation means that you find the value of that function at the desired point x. Okay, so now let's move to the process. So the process is pretty simple. Basically, you choose you sample an x value from the proposal distribution. So let's say you sample some x value from the q distribution, and let's actually picturize this. So let's say our distribution actually looks a bit like this time, right? So this is your desired density, and this is your proposal density, right? So your goal is to first sample from the proposal distribution. So let's say you choose this point, right? So you will sample this point with this much probability, and for this x value you will also sample a u value from the uniform distribution, right? So let's say we also sample a u value from the uniform distribution between 0 and 1, right? So the algorithm is that we reject this sample x. So reject x if u lies in the envelope between mqx and p of x, p tilde of x. So if it lies in this envelope, right, then we reject x. So this is the reject part, and otherwise we accept x, right? So this is the accept part. So reject x if it lies in this part, and accept if it's in this part. Acceptance probability will be p tilde of x divided by mq of x. So that's the probability that you accept a sample. Okay, so let's now try to show that the samples generated with this process are really from the desired distribution, right? So the samples x, so these samples are actually like after you reject or accept them, they become samples from the desired distribution. So essentially we're looking at this probability p of, so a random variable, like let's find the CDF of the conditional distribution, right? So this will make sense in a minute, but what we really want to find is p of x less than or equal to x, such that u is less than or equal to p tilde of x and divided by mq of x, right? So why does this probability make sense? First of all, notice that we are looking at the CDF, right? This is a conditional CDF, but we are looking at the CDF and we want to show that this CDF is actually equal to the CDF that we want, right? We want to show that is this equal to the CDF of p for a value of x, right? So is this equal to the probability that p of x is less than or equal to this value of x, right? So first of all, it's a PDF, and the other thing is that it's conditioned on the fact that the uniform variable is less than or equal to the ratio of the unnormalized density and the proposal multiplied by a factor, which is exactly the acceptance criteria. So this is a CDF conditioned on the acceptance criteria, which is in shorter process, right? So what really is this quantity? Let's actually compute this. So let's first try to open this up. So this definition, we can write it using the definition of the conditional distribution. So this is this p tilde of x divided by mq of x divided by p of u less than or equal to okay. So let's actually first compute the denominator, right? So what is the denominator? So let's say this is just 1 over 2, and let's compute the denominator first. So what is 2? Well, 2 is probability that u is less than or equal to p of x divided by m q of x, right? And well, how do we evaluate this? Well, let's say we first marginalize it out of another distribution, right? So if we had another distribution which was p of u less than or equal to p of x, mq of x. Oh, I'm sorry, so we should be using tilde, and x equals x. So we are trying to now make sure that this x becomes this x, right? So we can effectively say that this probability is from is found out by marginalizing this probability density, which makes sense, right? And now we can just open this up, and by opening this up, I mean we can write probability of u less than or equal to p tilde of x mq of x such that x equals x, and then, well, we will have a probability of x equals x, right? But what is that probability of x? It's the PDF of x for a value of small x, right? And what is the PDF? It's the distribution that we actually sampled from, right? So what is the probability that the uniform variable is less than or equal to this quantity? Since uniform variable is a number between 0 and 1, the probability that is between that is less than or equal to a certain value is that certain value, right? So if it were, for example, a probability between if it were the probability that it's less than or equal to 0.3, then the probability that it's less than or equal to 0.3 is 0.3, considering that it's sampled from a range of 0 to 1, right? So this thing is actually just p tilde of x by mq of x, and here the x are the values that this assumes, right? And the PDF is just q of x, because that's the distribution that we're sampling from. Okay, so what is this exactly? This is just, so the q's cancel, and we're left with 1 over m minus infinity to infinity p tilde of x dx, right? Okay, so, well, we can't really say what this sum evaluates to, because it's not the normalized density, it's the unnormalized density, so this doesn't really evaluate to 1, but let's leave it at this, right? Let's try to find second now. So second is, if you notice, p of x less than or equal to x, u less than or equal to p tilde of x by mq of x. And actually this is pretty similar to the first thing here, but you will see why. Well, the reason is actually that if you look at this just from the perspective of x, right, then this is a CDF, right? So because it's a CDF, it's the value of the PMF or the PDF summed or integrated from minus infinity to that value, right? So this is just p of x equals x, and then we keep in the other things, which are the u less than or equal to this quantity by this quantity, right? Okay, and this thing, if you notice, is very similar to this quantity over here. So can we evaluate this in a similar way? Yes, we can, and it will lead to exactly this result, except that the bounds of the integration will be different. So if you do this, then you will get minus infinity. So I'm skipping a few steps here, but if you do this, you will get minus infinity to x 1 over m, and then p tilde of x dx, right? And so what is okay, sorry, this was 1. Hopefully that doesn't cause too much confusion. So what is 1 divided by 2? Well, 1 divided by 2 is 1 over m integrated from minus infinity to x p tilde of x dx, and the denominator is 1 over m minus infinity to infinity p tilde of x dx. So what is this value really? Well, the m's cancel, and we note that this thing is the normalization factor. Actually, the normalization factor is the, like, if this were the normalized density, this would be 1, but if it is not the normalized density, then this is just z, right? The z that we started out with, the z. So this thing is just minus infinity to x p tilde of x by z dx, which is actually the CDF of the distribution that we wanted to sample from, the normalized distribution that we wanted to sample from. And this completes the proof. So we know that this process, when you sample x from qx and then accept or reject that sample with the probability that is p tilde of x by m q of x, where m is known, then you end up with samples from the desired distribution, which is the normalized desired distribution. Okay, so hopefully that was a bit clear, and thank you so much.